Sir, online series on Generative AI Masterclass from LLMs to Agents and Knowledge Grounded System. I'm Kishore from PALS Program Management Office. I'll be moderating this session today. I would like to reiterate the basic instructions once again. For easy identification, please rename your Zoom display name as college short name hyphen your name. Participants will be stay muted and allowed to unmute only during Q&A session. Chat box usage will be restricted. You can message the host or co-host. We will enable it only need basis. During this session, if you have any questions to be asked to the speaker, please write to askpalspmo@gmail.com. This mail will be monitored throughout the session. Ensure to write your name and college short name along with the question. Attendance link will be pasted in the chat box. Please use registered email ID to mark your attendance. Participants are requested to register in the Slido at the beginning of the session. Feedback link will be shared at the end of the session. I now request Mr. Pati Lakshmi Narayanan, PALS champion, to give the opening remarks and introduce the speaker. Over to you, sir.
Thanks, Kishore. Good afternoon, everyone. I feel you guys are definitely feeling great after 3 sessions. Most of you would have attended the 3 sessions already. This artificial intelligence is not something which you guys are seeing, especially students like you, seeing from the distance. This is just nearer to you. This is a friendly thing for you. And then many of you are already using it without knowing. Your Word document, if you're writing, it is correcting automatically, where artificial intelligence is there. Whatever you're using a mail is having a lot of guidance to say how to write the mail. And then you are seeing many things in Google or in Facebook where artificial intelligence is used to tell you what you have to see and then what you cannot see and then what is your interest, etc. So it is something which definitely as a tool, it will be another thing useful for everyone, humankind here. A lot of changes we have undergone and then we adapted, human being have adapted. This AI also we will adapt. So these sessions are very important for you to understand the concepts and then ideas, whatever you are telling. Probably you will be using it for your projects, internship, etc. If not, definitely you will be using for your career, your whatever work you are going. You cannot be spared from not using artificial intelligence. So please give good attention. You are getting one of the flagship program from IBM Research team for especially designed for PALS colleges. So you are having a last session today and then we are having Jaydeep Sen to take this one. In this one, the last session, what we are having today, the topic is Generative AI Master Classes. In that one, you will be session 4 is RAG based applications. So we are having now Jaydeep Sen, master inventor and manager IBM Research, who are joined with us to take and then educate us on all RAG, whatever we are calling as RAG. So thanks Jaydeep once again. Jaydeep Sen is a senior research scientist at IBM Research and manager of speech and language technologies. Jaydeep works in information retrieval, question answering, and related NLP applications. Recently, his focus has been creating state-of-the-art embedded models for retrieval and adapting LLMs for efficient knowledge ingestion, especially in Indic domain. He has more than 20 papers, tutorials in leading conferences such as UCIA, VLDB, SIGMOD, ACL, NAACL, calling, etc. Thank you. Jaydeep Sen, over to you.
Thanks, Pati sir, for the introduction, and very glad to be back here. I remember we did a session on last February that was also a very Uh, Very nice session for both of us. I hope that was useful for you, as well as there is a lot of learning opportunities from the interaction we had with the whole team. So very glad to be here. And so regarding today's topic, like Patisar already mentioned, the topic is around RAG and the applications, but I would start a bit more from the origin so that we can appreciate how it really evolved towards this. So I will spend some time around large language models, how it evolved, and finally how it is making itself useful in RAG applications, and how you can also use it so easily with the different technologies or models that are available now. Okay, so with that, I will start sharing my screen. I hope my screen is visible.
Hello. Tell me, I am attending this LLM closing remarks.
Oh, shall I start?
Yes, sir.
Okay. Okay, so I will talk about introduction to LLMs and then its evolution, and we will end towards RAG technologies. So what are the things we are going to discuss today? We want to just start with fundamentals so that we understand how it started. We can appreciate the direction it is taking, and that will also enable us to understand in a better way what exactly RAG is, how it is helpful, and why do we think that this is going to be something which is going to stay for a longer time now. I will talk about the traditional fine-tuning method, how the LLMs came into picture. With respect to LLM, what are the alternatives of the full fine-tuning, then touch upon instruction fine-tuning, then generate using LLMs. And then, as I mentioned, I will touch upon RAG, and also I will take you through a very simple kind of use case or an exercise how you can also use RAG pretty easily with off-the-shelf models. So starting with fundamentals, we have been discussing about large language model, but let us first quickly understand what exactly a language model means. So as the name suggests, it's basically a statistical or probabilistic model that is trying to model the ideal probabilistic distribution of a language that is really spoken by humans, let's say. So what do you really mean when I'm saying like it is essentially trying to model the language or the probability of the language? It basically is like this: given any sequence of words, this is a model which tries to predict that whether that particular sequence of words makes a valid sentence in that language. So like the examples you have seen here, a quick brown dog or dog quick a brown. Between P1 and P2, obviously P1 is a more valid sentence than P2. And the main idea of language modeling is to be able to do it via a model. So like as humans, we will be easily able to tell that, oh, P2 doesn't make any sense, but P1 does. We need to do that via a statistical model, and that model is called language model, that figures out that the probability of P1 is much larger than the probability of P2, greater than P3, greater than P4. You can literally see like how these are like different, even incoherent words, right? So these are even less and less probable. So that's what language model is. Now, regarding the tooling, so how does a language model typically gets produced? Predominantly over the last 4 or 5 years, at least I can say, the community has completely shifted towards transformer-based mechanisms. So that's why I thought we can just give you a very brief glimpse of transformer. Don't worry about technical nitty-gritties. I will purposefully try to stay away from that, but just give you the conceptual parts that you need to understand and appreciate the things that we are going to talk about. So when we say transformer, it's basically an encoder decoder model. If I break down the encoder, it is further divided into multiple blocks of the similar encoder. The idea is you get an input to the encoder, it goes through all the encoder stack, creates a representation. When I say representation, it's basically more of a embedding in the vector world that is not necessarily human interpretable, but something that the machine can understand and make use of. So it gets the embedding and goes to the decoder. So decoder makes use of that embedding or the vector, and then produces some output that based on the task that you are trying to make use of this transformer model. Now, so even at this point, just have this thing in your mind, like this encoders are typically used to take a natural language sentence. Let's say if we are talking about NLP, which is the focus of our discussion today, it takes a natural language sentence, something that we humans speak, and transferred it to something that the machine understands. That's that intermediate vector. The decoders basically, from when it is working in an encoder decoder setup, it takes those machine understandable parts, or how the encoder really understood the human input that was given to it, and then tries to transfer it back towards the human interpretable part by producing the natural language output. That's how encoder decoder models work. A very key innovation in the transformer here was the self attention mechanism. And if I try to give you a very high level intuition of how this works, it is basically given a sentence, it is trying to establish or attribute relative importance of other words into understanding what a particular word mean in a sentence. So in this example, this sentence is the animal didn't cross the street because it was too tired. You see, the word it is having maximum attention from the animal, which basically means that it is referring to the animal. Therefore, when you are trying to decode or understand the statement, the emphasis of the word it is mainly coming from the animal. That's what it is trying to capture. And there are this nuanced way of learning different matrices and matrix based operations, such that when you are trying to produce representations of each of these words, this is the conceptual thing it is trying to capture, how the other words are influencing the meaning of that particular word. That's what self attention is about. So encoder decoder models as a black box, this is how it looks like. We started with this in the initial diagram also. You give it an input, the encoders transform the input to an embedding, that embedding goes into the decoders, and then there is a task specific layer that can produce some natural language output, which is back at the human realm. Now we want to make this distinction right now, because this will be useful. So traditionally the transformer model was encoder decoder model, but there are two variations of it. There are encoder only models, which only cares about start with an input, create a representation. So it is not essentially trying to produce a human readable output. So it creates an representation, and so this is the left hand side of the things, and these representations are often very useful for multiple downstream tasks when you are trying to club it with some when you are trying to basically club it with some, let's say, an application or task specific layer. We will just see it in a next slide. And then there are also decoder only models, which basically doesn't rely on the encoder intermediate embeddings anymore. It starts with the natural language input, and it learns to make use of the natural language input through its own neural network layers to produce a natural language output. So this right hand side is more of a decoder only models. OpenAI or many of the today's large language models, they are predominantly decoder based modeling. Where at the left hand side of the things, which were encoder based models, these are its own vertical, where these are the focus of creating more and more robust embedding models. And there is one difference between these two is typically the encoder models use attention in a bidirectional way. Remember when I was discussing attention, it basically means how the meaning of a particular token is getting influenced or attended over by all the other tokens. Bidirectional means the tokens left from the token in question and right from the token in question, all of the tokens are contributing to figuring out the meaning of that particular token. Whereas for decoder only models, it is typically unidirectional. So you might have also seen this term autoregressive, that basically means as you keep decoding, only then you get to know the future state. So here, as you see, the attention is only from left to right. So En gets attended over by all the tokens, but not E2. So E2, the representation of E2 is not having any input from En. It is only seeing what E1 was. So that's the difference in the architecture. Now, talking about trying to take this transformer models and put that into task. So these are just an example of various different tasks that can happen, and these are all BERT based. So you basically use an encoder model to create an encoded representation, and then you try to learn a task specific layer on top of that encoded representation. And that actually can be any task, like sentence pair classification. You are trying to get the decision out of the representation that was created from the CLS token, which is a specifically designed token to capture the meaning of the whole sentence. Similarly, for single sentence classification task, or even let's say question answering task, where you typically try to learn a classification layer on top of each token to signify whether that token is a start token of the target answer span or the end token of the target answer span. So what it basically, this diagram, the only takeaway I want you to take from this is this encoder only models can also be adapted towards various downstream tasks based on the embedding it produces, and that happens via a particular task specific layer that you want to train on top of the encoded representations. So talking about fine tuning, traditionally how fine tuning has been working, let's see, if I want to use the same formula here for the transformer models, this is what it is going to be, right? Like I explained, there is a transformer model which is having multiple encoder blocks, let's say, or even transformer blocks. And then there is a way how you are trying to use the representation for an end task. And in order to tune that, you ultimately tune all of the transformer network. So this red dot is the back propagation that is coming from the final task specific signals or the goal data on which you are training. And that actually makes you basically propagate the gradients back to all of the transformer parameters. Now, typically, if let's say if you're trying to tune a transformer network for 3 different tasks, because you are essentially changing all of the parameters of the transformer, what would mean is it would need, if I'm working with 3 different tasks like translation, summarization, or table to text, that means I have 3 different models of transformer, each specifically tuned for a certain task. And because you are changing all of the parameters, you need a fresh copy. So they are like 3 different models. Although their base was initially shared, but now they have diverged. So you need a lot of storage space in terms of storing 3 different models. And now this is where it starts becoming a problem, at least in the LLM era. And we will see how. So when BERT came, I remember it was dubbed as an LLM. LLM is standing for large language model. And the reason was it was like a model that was using 110 million parameters and it was having 12 flavor in the transformer. The BERT large variation had 340 million parameters, 24 layer in the transformer. But fast forward to this day, even there are even more voluminous model than this. But GPT-3 itself is 170 billion parameters, starting from where we started like 110 million or 340 M. So imagine if I'm trying to tune GPT-3 model for 3 different end tasks and I'm having to maintain 3 different copies of it. And 3 is just a number here. It can be anything like 10, 12 downstream tasks that you care about. It starts become prohibitively expensive. You cannot just keep storing like 175B models for n different tasks separately. And this also kind of shows up in the number of tokens it needs. So the more parameters you add to the model, the more data hungry it becomes. So for example, BERT, it was a very good model at that point of time, and even now BERT is heavily used for different tasks. It started with 3.3 billion training tokens, and compared to that, GPT 3, which is like it has seen 300 billion tokens already, but it is only consuming like what 60% of the common crawl data, only 3% of the Wikipedia data, which basically means like there is lot and more data it needs to see as compared to where we started. So it's not easy to kind of keep seeing that volume of data and then again start from scratch when you are trying to train it for a different task. And in terms of the computation it needs, you can clearly see how much of a rapid change it has gone through. So this is like training petaflops per second days. So BERT model, assuming that it does a petaflop number of float point operations in a second, it needed like somewhere around 2 or 3 days for the BERT training. The same thing now takes around what I think 5,000 days. And imagine this is a huge computation. You are doing petaflop of floating point operations per second in a day, and even then you need 5,000 days. So typically this is where we call as the scaling wars, because this amount of scaling is not easy. It comes with a lot of engineering challenges, and it also means you have to invent something beyond the traditional fine tuning, because you do not have the luxury anymore that you can keep tuning this model from scratch repeatedly. You can keep storing these models in multiple variations. That's simply almost near to impossible now. So this is where, in fact, now probably a pertinent question to ask: why do we even care about LLMs then, if it is so difficult to manage? What is the plus point? What is the strength it is bringing with it? And the answer to it lies in the very first GPT-2 paper, which was kind of a, I would say, surprise, or the community was awestruck but by what it proposed. It proposed something brilliant. It was a game changer at that point of time. Now, of course, it has been widely used in context learning. So the basic intuition, where did we start from it? So the intuition was, why do we expect LLMs to be very good? Because it has seen tons of data. It has digested world knowledge in a very good way. It can kind of, you can imagine like it's that machine. If you think, if you throw it anything that needs some information access, it can do it in a jiffy. But now the question is, can I do it without fine tuning? And the key to that answer remains, probably there is a hope of doing it without fine tuning if I can phrase my end task, or if I formulate my end task in a way such that it is natural for the LLM to behave the way I want it to. So how does a LLM behave? The LLM, because it's a language model, it is trained for the task that given an input sequence, it is going to predict what is the next thing, what is the next word, or what is the next sequence of words that is going to come out of it. Now, if I have to take any end task and make it formulate in this setup, which the LLM is so habituated and very well at doing it, this is the notion of prompting a pre-trained language model comes from. So you're basically trying to take a task and convert it, formulate it such that it becomes a prompt to the model, as if now the model doesn't need to behave anything different. It needs to behave exactly for the task, which is language modeling, that it is trained for, and you will still be able to use it to get what you need to do with it. So this is an example. If let's say I am supposed to do a sentiment classification kind of task, the encoder only models would have needed you create the embeddings, then train a layer on top of it to detect a sentiment, right? But in this case, what I am doing is I am utilizing the inherent capability of the model to do very good language modeling, to formulate the sentiment classification tasks as if it's a language modeling task. So I'm starting with no reason to urge. It was then letting the model fill in what is the mask thing, which is the usual autoregressive decoding. And it will then fill out something positive or something negative that you will be easily able to take out, and that solves your task. And GPT-2 actually showed that this is not one of fluke things, but this it can do predictably well across a diverse set of use cases, diverse set of data. And this was surprising because when someone was training the model, no one really thought that this will be the use case of the model. But here we were seeing that there was emerging capabilities coming out of the model where it was able to do this. It was able to respond well to a nicely structured prompt. And you can literally do anything, or I won't say anything, but a lot of things nicely by prompting the model well. So for example, this is as complex task as a question answering. You are prompting it like this is a passage, this is a question, and then you are asking it to fill the model what will be the answer, but then it does so quite easily. So that was the first emergent zero-shot learning probability of the GPT-2 or decoder, GPT-2 like decoder only models, which are like large language models, and it is showing you don't need to tune it, just prompt it nicely, and in zero-shot setup. By zero-shot, it means You haven't seen any of the domain data, you haven't seen any of the task specific tuning, but the model is able to do what you want it to do. So next came few shot learning. So as you can see in the figure, the idea was, if I keep showing model some examples of what kind of tasks I need the model to solve. Like these are the spell correction tasks, right? Misspelled goat to corrected goat, misspelled snake to corrected snake, things like that. This is a task of translation. Thanks to merci, which is a French word. Hello to bonjour, which is again a French word. If I give some of these examples, can the model really pick up the signal that, oh, I'm hinting at this task and perform the task for me? So that is basically the next revelation that came in GPT-3, um, which now is dubbed in the community and heavily used and in context learning. The basic idea is you are giving enough examples for the model to know what task you are interested in, and then letting the model solve it for a particular data points that you are interested for. And this is where the curve really look like. So if you just prompt the model that translate English to French and you give it a word, it started somewhere here. If you give it one example, this is that one shot, it immediately jumped from 60 to 70. You keep on showing it more examples, it starts improving more, to the point that you see it has crossed what the fine-tuned BERT was. Like remember the initial slides where I showed like you can take an encoder model, do a task specific tuning. That is this line. And here you don't need any tuning at all, no gradient updates at all. But this model, just by few shot prompting, surpasses the performance of a fine-tuned BERT model. And this is a similar diagram which is also showing you the picture like how zero shot, one shot or few shot evolves. Typically few shot is always working better, and it can suppress fine-tuned SOTA, not just on very small or kind of anecdotal data sets, but as established data sets like trivia QA, which is an important data set for trivia based question answer. And this is where, so all of this that we are discussing here so far, these are base models. I will come to the terminology why we are calling it as base model. So we are calling it a base model because this model is traditionally being fine-tuned for language modeling task only, nothing else. So Granite base model is a base model offering from IBM, and you see like this does cater to different kind of tasks, different kind of domains, and it doesn't need to have any domain specific tuning. That's the beauty of this. And you see these are kind of catering towards mathematical things, code, human exams, common sense, reading comprehension, reasoning, and the Granite model typically suppresses all of the existing competitors. And still, this diagram that I'm showing is few months old. You can look at the latest Granite models and even the better offerings that we have there now. But the idea is, so there is this forte of base models which should be usable as it is with few shot prompting. And IBM does offer a very strong suite of base models that we call as Granite in different parameter counts. This particular one is an 8B example. So now the question arises, so is there a limit to it, this prompting trick that we are using to use off the shelf language models? So there is an example where it starts showing that there is limits to it. For example, if I want to solve, let's say, this calculator kind of thing by using a model, can I just keep showing it some example and hope that it will do it here? Turns out, no, not all tasks can be as it is this, because some of the tasks need more of an internal reasoning. It is not easy to pick it up just by in context example. So what is the solution? That means like we need to play around with the prompt. We need to figure out what is a better way or more involved way of prompting. And that gave right to this idea called chain of thought prompting. So here you see the question is around, it's testing some mathematical reasoning ability. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? And So this is an example. This is an in-context example. If you had given just the in-context example, which is showing just the answer, but not the explanation, turns out the model is not able to pick it up from there. But if you change the in-context example to also give the reasoning how 11 is the right answer, the model is able to pick up what you are asking it to do. And even in its output, the model does produce the reasoning, and then only it gives out the question. So this is an example where it is not a trivial prompt, but it was a find from the community to figure out that, oh, the prompt can be more involved. It can purposefully elicit reasoning such that it tailors the model's output space to be closer to the real outputs that we need. And that basically opens up a larger question. Should we rather tune the prompts for LLMs? And this is one of the next things that happened to the LLM world, which was prompt tuning. So this is the idea. We want to avoid full fine tuning of the model, because remember, this is prohibitively expensive. You are just using too much of resources for a particular task, and if you are not able to share it across tasks, then it doesn't make any sense. So instead, what we do was, the pre-trained model is nicely modeling the conditional probability of auto-regressing token generation, like y given x. We try to tune the model for a certain task, but with a very important distinction. I am not going to touch the core parameters of the model at all. So that theta is fixed, but I introduce a theta p, which is specifically for prompt tuning. And that is much, much lesser than the whole parameter space for the model. And I only train that theta p such that it basically tunes the prompts that is useful for the model. So this, in the diagram, as you see, this is pre-trained model. The parameter space for the pre-trained model is completely frozen. Then there is a tunable soft prompts. Only few of the parameters are getting updated, such that instead of manually trying to provide the prompt, you leave it to the model or this parameter space to figure out what prompt really is going to work for my task. And that is called prompt tuning. And this, as you see, this is not just competitive, this is actually superior. And to be honest, there is no surprise here. Because if you leave it to the model to know what works best for the model is obviously going to pick from the search space for which its embedding or its own parametric knowledge is much more closer to performing the task. So if so, the prompt tuning, the prompt design, which is the blue curve, is where you are trying to manually engineer a prompt. The initial few examples that I showed. Prompt tuning is this, that I'm not trying to manually manufacture the prompt. I don't even care whether my prompt is, the prompt that is getting learned is interpretable or not. These are kind of soft tokens. By soft, I mean, like, this may not be hard prompts which are interpretable by humans as language tokens, but this can be just as a representation. This not only does much, much better than prompt design, it really catches up with full fine tuning of the model. So literally kind of alleviating any concerns or any need that model fine tuning might still be a very important skyline. Uh, I mean, it still is a skyline. It's expensive. We cannot do it, but at least it is a very good news for the community that we can still live with very optimal performance just by prompt tuning without caring about model tuning, because it finally starts catching up. There are different variations here. Obviously, when you are trying to do prompt tuning, question is, how do you want to initialize the prompts? Some of the studies are showing that a better initialization typically gives you better jumps. But there is also this thing that as you keep on increasing the model size, it starts becoming uh, unimportant. So if you are working with smaller model size, your initialization strategy is important. That will give you better convergence. But for longer model sizes, they kind of eventually catches up irrespective of where you start. Similarly, for prompt length, again, there is a difference in trend between, are you working with a small, relatively small LLMs or large LLMs. For large LLMs, even as few as one token is kind of good enough. It tries to catch up. But typically for relatively shorter LLMs, it has been seen that if you try to increase the number of tokens that you are trying to optimize during prompt tuning, the performance improves, but it kind of starts plateauing around 20. There is after 20 there is only diminishing gains, so that's not too much used. So this is the summary of prompt tuning. Remember, we started with a pre-trained model. We manually engineered prompts, that was prompt design. Then the other extreme is you are trying to do the full fine-tuning of the model, that I said, like it's almost impossible to do nowadays with large language models. And prompt tuning is that perfect bridge that basically tries to do tuning, not relies on human manufactured prompts, but it almost catches up very nicely with model tuning. Both of them show quite strong performance. Okay. So now coming to the other style of instruction fine tuning and the world of all the IFT models. So why there was even a need for it? So all the thing that we have discussed so far, manually manufactured prompt or leaving the prompt to be tuned, then again the same question, is there limits to it? Turns out there are. For example, if I try to give this, explain the moon landing to a 6-year-old in a few sentences, and it doesn't really do a good job if you're trying to throw it to a base model. And if you introspect, it should not come as a surprise, because remember, our whole idea of prompting was trying to take a task and formulate it as if it's the natural completion task for a LLM, which it knows so well, given the humongous amount of data it has seen. It is well habituated in completing sentences. That's what the major motivation of prompt, to be able to prompt LLMs and get your task out of the box without needing any update. But this is more than a task. This is more of an instruction. It's basically you want the model to do something, and which is not easily transferable by an auto completion task. And this is the examples, like if you try to treat it as an auto completion task, these are the natural kind of completions that the model is doing, because the model has no idea that you are trying to let it perform a different task. And that's where instruction fine tuning comes in rescue, where you try to tune the model to interpret, understand instructions, and act on it. So this is how it kind of happens. So there is the prompt, and then you actually give a completion, which is less of a autoregressive completion, but more of following the instruction and giving out a respectable output. And now this is that kind of data. Someone might say that, yes, it still looks like the traditional fine-tuning data. You are just having some instruction and their responses. I would say true, but there is an important conceptual differences. The difference is, in traditional fine-tuning, you fine-tune for a particular task, and you have to gather tons of data, specifically if you're working with large language models, tons of data on that particular task to let the model know that how to perform that new task that the model didn't know to begin with, let's say. In this case, instruction following is a different thing. You are not trying to tune it for any specific task. Here, the idea is you are trying to tune the model for understanding instructions. And when you are trying to let the model understand instruction, you have to vary at the instruction level, so that the model sees plenty of different instructions and the way to act based on those instructions, and it can generalize understanding or interpreting instruction and acting on it. So this is the key important distinction between instruction fine tuning. It is on many tasks, and the data is not for a particular task. It is across tasks, across different instructions. All you are trying to teach the model is how to understand an instruction and act on it. This is also an example which should nicely show you how exactly this is getting done. So these are like, please answer the following question. This is a question answering example. It goes to the language model, and there is an answer to it. This is another different instruction. Answer the following question by reasoning step by step. And this is also going to the language model, and this gives out an answer. Now, if you have a different mix of instruction and their responses during the training phase, here the task essentially becomes how the language model learns to interpret the interpret the instruction. And what it basically means is, once you have done a good job at around instruction tuning, at this time, it can now respond well to a new instruction, which may not have been seen during tuning. So in this case, for example, the instruction reads different. You are just starting with a question, then you are following it up with an instruction, give the rationale before answering. One might say that this is in principle similar to this, like you are asking the model to reason. But see, the phrasings of the instruction is entirely different. And still the model is able to do the good job. The reason is the model has learned to parse instructions and understand and know how to change that to an actionable output, which is this. So, and it actually makes a lot of difference in practice also. So I have taken two models. It's kind of old model, but the example still fits. So there is this UL2 from Google and FLAN UL2. The difference is FLAN stands for a large suite of instruction fine tuning that went on top of the UL2. So UL2 is a base model. FLAN UL2 is an instruction fine tuned model. Now, if I try to kind of ask this, that look at the below sentence and generate a follow-up sentence which contradicts the below sentence. This is exactly kind of opposite to what the typical task completions are, because task or typical sentence completions are in language modeling. Because in language modeling, you will try to complete the sentence with coherent things, right? And in this case, I'm specifically asking the model to do just opposite. Now the base model, as you see, it cannot do that well because the intent is so different from the language modeling task, right? So it keeps on blubbering the same thing. It's a beautiful day. It's a beautiful day. And it doesn't really contradict. But in case of FLAN, once I give it this instruction, it tries to understand the instruction and it tries to produce something which probably contradicts. So it's a beautiful day today and it tries to say it's a rainy day today, where I mean, at least in those language modeling which were initially pioneered by the Western world, a rainy day is not a very good sign for a good day. Typically they consider nice sunny day is the notion of a beautiful day. Okay, so rainy day is kind of a contradictory towards a beautiful day, and it is able to understand the instruction and act on it. The base model cannot. So it's a clear example, a very rudimentary example that really shows there is a clear difference between a model understanding instructions and a model cannot. So that's the difference between base and instruct. And so again, IBM has a suite of instruct models as well. And here you see, along with the other things, there are more different dimensions getting added. Instruction following is a very important feature for instruction tuned model. RAG, function calling, these are basically more towards something that you want to achieve from IFT models that the base models cannot give. And like the previous base model versions, these are also, it's better than its competitors. Again, the same caveat, you can go to the website and see the latest suite of models that IBM has. This slide is still at least a few months old. But yeah, this is one of the better models in the competitive landscape there on the similar size segment. This again shows the exact the comparison between base models and instruct models, and it's across like 19 tasks and 6 domains. So it's really generalizable. It's not really sticking towards a particular task or domain. So that's the beauty of these language models. Okay, so I think now we have covered all the necessary things to really touch upon RAG. So RAG stands for Retrieval Augmented Generation. So let us see why that is needed. So this is needed because consider this simple use case, number of area codes in New Hampshire. And let's say I'm going to use a large language model out of the box. Like this is my question. I expect the model to give me answer of it. And it does produce an answer. There are 3 area codes in New Hampshire, 603, 617, 857. Now, from a language modeling perspective, this answer looks correct because there is no grammatical error. There is no problem with the fluency of the statement that would make you doubt that, oh, is the model being correct versus not. And typically language models are for this. It is supposed to produce very nice coherent sentences, and it is doing it. Except the problem is this answer is not correct. It's not factually correct. The actual factually correct answer is 603. And this is where RAG comes into picture. The idea is when you are passing the particular question to the black box LLM, don't just pass the question, but also pass the relevant documents which is having information to answer the question. And then the LLM is much better poised to utilize that information and give out the answer. And this is also something that in the community you might see these terminologies like parametric knowledge or internal knowledge versus external knowledge. Now, RAG was a key, how do I call it? A key new dimension in this. The reason is all the while, whatever we have been discussing so far, we have been trying to utilize LLM's parametric knowledge to do the task, like whatever the LLM has learned during its training. But in this case, it is trying to free the LLM from trying to remember every minute details of world knowledge. Rather, use an external knowledge base to figure out what are my important documents and then conditioned on that document, produce an answer, which is a much easier task for the LLM because it has been tuned for so many different tasks, question answering being a very prominent one there. So this is where retrieval augmented generation came into picture. And from this diagram, you can easily make out the meaning of the name. So this is the generation part, but this generation is augmented by the retrieval. So the retrieval is helping the LLM to generate better. So that's why it's called retrieval augmented generator. And there are two parts to it. One is the generation, the LLMs, and then there are retrievals. DPR, Colbert, these are like some state-of-the-art methods that uses embedding. But the key part is this also connects back to the encoder-only models that I started with, which I mentioned that these are the models which tries to produce embeddings. And one of the key use cases of embeddings is trying to retrieve similar documents which are very close by in the embedding space. So that's where encoder-only models become very handy. So there is a retrieval part here, there is a generation part here. And this is the same thing you are going to see, like a lot of advantages, disadvantages. I would say RAG doesn't have a disadvantage other than adding an additional component, but it has been always proven to be much more useful. So there is this information retrieval. The usual text generation is a closed book exam, like you don't get to see the book in the analogy. But if you are allowed to see the book, you can actually open the book, locate the information, and then apply your reasoning and all the skill that you need to figure out what the answer would be. And this is what retrieval augmented generation is. And these two terminologies are also very oftenly used in the community. One is closed book exam, one is open book exam. Open book exam is the RAG part. That's where opening the book means you are letting the retrieval retrieve the right documents for you. And it basically opens up for the unlimited knowledge. Why I say unlimited? Because you are no more bound by what kind of training data was shown by the model, because we are no more bound by the parametric knowledge of the LLM, but you are leaving the exact knowledge source to be retrieved by the retriever. So as I mentioned, it has two parts to it. One is retrieval, one is generation. The retrieval typically is from the embedding models. And this embedding models takes, let's say, queries, let's say documents. These are all textual inputs, but it creates a vector embedding. And a vector embedding, storing the vector embedding, managing the vector embedding and operations over those vector embeddings like similarity search, approximation-based search that can run quickly. You need a dedicated vector DB, and there are so many options here. I have just listed a few of them: Pinecone, Milvus, Quadrant, VV8. There are more, but the main idea is you basically given an input, you create an embedding, you store it into that vector store, and that vector store works as an interfacing point from your application world towards those vector world where you want to, let's say, do similarity search. That is most often the case. Now, in order to really deploy a RAG pipeline, there are some little nuances that we should just be touching upon before I take you through an example. So you start with a set of documents, right? That is your search corpus. You start with a set of documents such that for an incoming question, you search on those documents, you get the right document, and then you pass it to the pass it to the LLM for generation. So these documents are often, it can be quite large, right? So the first step is obviously the loading the documents. Now there is this splitting the documents, which also you have heard about the term chunking, which is so often used. There are different strategies about what are the different methods or optimal ways of chunking. The idea is you need to chunk because the encoder only models for a long time only supported a certain context length, like 512 being the prominent examples from BERT days. Of course, there are new age upcoming models which does support higher context length. Even IBM has it. We call it R2 set of models which supports 8K context length. But traditionally, remember when the RAG pipeline started, the embedding model could support a context length only up to 512 tokens. That means you cannot pass the full document towards the embedding because most of the document will get truncated. The embedding won't even consider that. So you needed to do a split, you needed to do a chunk. So every document was split into different chunks, and then these chunks were embedded. Because the chunks were well within the 512 limits, and those embeddings are getting stored towards vector store. And when a question arrives, you basically do a retrieval. That retrieval retrieves the specific chunk for you, and then you prompt an LLM with this question with the retrieval chunks, and this LLM receives that prompt as an input and finally produces the answer. So this is the retrieve then generate or RAG framework. Now there are different embedding models IBM has. These are all available in watsonx.ai. This is basically an IBM platform where you can easily instantiate different RAG pipeline, touch different state-of-the-art models and use it. In fact, I will take you through quick like 7 or 8 steps, as easy as writing a couple of lines in each step to do that. These are like different models watsonx.ai holds. IBM has a very recent upgrade as late as last week where we came up with R2 set of models. This is where we are saying like it supports higher context length. These are even more robust model. And these are also available in public. So we have open source those model. You can directly use it from Hugging Face as well. So with that, now I will take you through using watsonx.ai to instantiate a RAG pipeline and show you really how easy it is for anyone, literally anyone, to start on it and try your hands and see something working for the first time in RAG. Just a quick recap of the pipeline. This is the question. This goes to search over a company docs, like this is the vector store. You get the results. This is the input. There is a prompt. There are the search result, and there is a question. It goes to the foundational model or the LLM, and it is going to give you the answer. So this is the pipeline that we are going to implement. So first is I am going to kind of create an watsonx access account, which is it is going to give me an API key, and I'm going to import that API key. And then I'm going to use a text loader from LangChain. So this text loader is loading the documents. Okay, and these are all libraries which are already available. It doesn't need you to write much other than these 4 lines, which are just pretty intuitive, or you can just look up to the manual of these libraries and these functions will show up right at the top. Like these are more or less helper functions, nothing much. So you are loading the text and then you are applying a certain text splitter. You are saying that I am interested into doing 1000 character chunks and I don't want any chunk overlap. That's all this is saying. And this text are already created those segments. This text data structure will be having the chunks that you want to index, and you never needed to write any custom codes. You are just using off-the-shelf libraries. Now you are querying the watsonx.ai to see what all embedding models are available. So these are different embedding models which are available. In fact, the list has grown now. In this example, I'm going to take this particular model, Slate 30M English Retriever. So this is what I am instantiating, that I am trying to utilize again a class already built in for me, watsonx embedding. I'm telling that I'm going to utilize this particular embedding model, same URL, API key, and the project ID that I created. And from documents, so remember the text I created from my LangChain, I'm just passing those text and this embedding class that I created, and it gives me a vector store created out of it. Here we are using the Chroma library. Then another foundational model, the LLM that we want to instantiate. So I'm instantiating Granite 13B. These are different tweaks or knobs you can say in any LLM to configure the performance you need here. So I'm saying like I would be using a greedy decoding method. I would be at most generating 100 new tokens, and the stop sequence should be end of text. So remember, now I have already instantiated an embedding model. I have used that embedding model to create a vector store. And now I have just instantiated a particular LLM. So now I just stitch the particular, stitch this together in a RAG pipeline. So this is that LLM that I create. What's an LLM instance, again, a built-in class for me. And then I say retrieval QA from chain type. I am using this LLM. I am using this retriever from the doc search. This is what the vector store that I created previously. Chain time stuff just means whatever I am trying to get from here, this will as it is be passed to the LLM along with the question. That's what this particular enum means. And this is an example. This is a particular whole document. This is in my search corpus. So obviously it will be chunked and divided into different chunks. Now I have ingested, let's say, this document, and I am going to ask this query. What did the president say about Ketanji Brown Jackson? And this is the result that is coming out of it from the whole retrieval QA, that is retrieval followed by the LLM based answering. And you see here, this is indeed the case. I have highlighted in green. This is the part of the retrieval that is helping the LLM to generate this answer. And out of the different chunks that was created out of this long document, this particular chunk was retrieved by the retriever, helping the LLM produce the right answer. Okay, so this kind of concludes the example how you can use RAG with off-the-shelf model. And if you really see, there are these 9 steps. Each of the steps, none of the places you are trying to write your own code. You are just using off-the-shelf libraries, off-the-shelf model, and stitching together existing API calls or library function calls. And that lets you create a RAG pipeline and really start working with it. So yes, this is where I would stop, and happy to take any questions. Any questions we have in the forum or?
Kishore, can you instruct them how to ask questions? Or if you have any questions in that Ask PMO?
In Ask Pulse Memo, we didn't receive for few participants. The chat box is open now. You can type your questions in the chat box. I've just opened the chat box. Participants, you can
Also
type your
raise a
questions in
hand.
the chat.
Kishore, can they raise their hand and we can unmute and make them
Yes,
ask?
yes, they can raise and we can also unmute.
Yeah.
There is a question from MEPCO, Parshika. Some evaluation methods for RAG SLR.
It depends on basically, is it an extractive or abstractive QA, but more often than not, typically we go for abstractive QA. So root scores, which tries to measure the n-gram overlaps between your generated answer and gold answer. Root scores or likes of that, for example, BERT score, these are some useful metric. Of the late, there has been a lot of usage towards LLM as a judge being a metric. That is particularly useful when you don't have the luxury of a gold answer. So if you just have a corpus and some question where you want to evaluate your system, you don't know what the gold answer is going to be, then you generate using RAG, then and use a very large language model, which is quite good, let's say, with much more parametric knowledge or world knowledge. and asks the model to judge the answer that you are giving on a scale of 0 to 5, and typically 4 and 5 are considered good responses. So these are typically the measures that we use in RAG.
Okay. The continuous question is how to verify the retrieved document chunk or relevant, sir.
So there is this for retrieval. Whenever you are working with a retrieval benchmark, typically you should be having the gold chunks that needs to be retrieved, and the measures are like recall at 5 or recall at k. There is even a more robust metric called NDCG that also takes into account the rank on which those documents got retrieved. Like your first document or your top document really came at 1 or it came at 3. There is a metric there is a change of measure depends on that. So BEIR is BEIR. BEIR is a kind of de facto known benchmark for retrieval. It has those metrics integrated into those scripts. And the idea is like if you're trying to measure retrieval, the direct way of measuring it, you should be knowing the gold chunks or gold documents which are relevant for the question.
Okay. The next question is from Albin. How image are passed to model base 64 clip model?
So, Albin, I am no expert on the image part at least. So, take my answer with a pinch of salt. It might not be the most accurate picture now. But as far as I know, how any of this model typically work, even including multimodal model, uh, always there is a conversion between what is the ground reality. For example, in NLP, the ground reality is the text strings, right? It gets converted in an embedding before it is in a space that can be operated by the LLMs. Same is going to be the case for images. It needs to be transferred into some embedding which had its own embedding model, the image world, and then it gets consumed by the LLM. So that's what my guess would be. But like I'm saying, I am not 100% sure if I'm completely accurate here or if there are some latest thing that has come up in the image community or vision community.
Okay. The next question is from Money. From where should I start? Like from core concepts, sir. Like max is important. I do.
Uh, okay, so there is a lot of mathematical background that is needed here. But having said that, I won't deter you saying like it's such a strong prerequisite that until you understand it, you won't be able to understand any other thing. The only part of math which you need to understand it well enough is the linear algebra part and the, let's say, the derivative part, so that you can appreciate the back propagation. So maybe I will say if you have time, start with those core courses. If you don't, then just start with a primer that lets you understand the idea, why exactly derivative gets computed, how a derivative gets used in backpropagation, and you will be at least set up to appreciate how different algorithms work in the LLM work. And once you have that, then you take basically either the BART paper, the transformer paper, or the Patrick Lewis rack paper. These three will be giving you the basic milestones on which every other technology has been built.
Thank you, sir. The next question is from Aruna Tamilarasu. How is file prompt turning different form of prompt engineering?
So these are slightly overloaded terms. When we discuss about, or strictly speaking technically, when we discuss about prompt engineering, there is a human aspect to it. Like you are trying, there is a trial and error with different prompts that you are trying and then fixing on one prompt based on your own observation how that particular prompt is behaving. That's prompt engineering. And therefore, because there is a human involved in it, the prompt engineering by design is always means it's a human readable prompt. Anyone who is working on your prompt can further modify it to suit their need. Prompt tuning is trying to take away the human interpretability aspect out of it. There is no engineering happening there, but you are leaving it to the model to learn what kind of prompt is best suited for the task. And that prompt is a soft token. It's basically at a representation space. It's not human readable prompts.
Yeah. Next is what is ASI?
I don't know what is ASI. I know Archaeological Survey of India, but what is in this context?
Okay, and the next question is where can I do customization sync? Sorry, missed the question. Where I can do customization sync, we depend on many of the self models.
Okay. So, if you are using off-the-shelf model, like I said, the best bit of customization should come from prompt tuning. At least that is the traditional school of thought for LLMs. But having said that, and by the way, if you are interested in prompt tuning, again, watsonx.ai has off-the-shelf capabilities for doing prompt tuning on your end task. But there are very recent efforts in the NLP community to do it in a different way. For example, if you have heard of knowledge infusion, that's also ideally a way of ingesting external domain knowledge into the model parameters without trying to take the trouble of tune the model that much. So I would say start with prompt tuning and read about literatures on knowledge infusion, knowledge ingestion, knowledge injection. These are like three terminologies which are used quite interchangeably in the community.
The next question is I want to build a RAG chatbot. I want to I want the output to be text plus image. Relevant most appreciate. Image should be relevant most appreciate. How should I approach it?
I want to
Roughly.
build a RAG chatbot. I want the output to be text
Text plus
plus
image.
images. I think you should be utilizing multimodal models. By multimodal models, I mean like the models which doesn't only feed on text but is capable of feeding on images as well. I think GPT 3.5 does it. That will be your best bet to do this kind of stuff. And on top of it, if you feel like it is not doing as expected, then all the methods of customization are open for those models as well.
Yeah, money has come with the abbreviation
So,
artificial super intelligence
so this
ASI
is
stands for.
basically okay. I know this term more as AGI, artificial general
Yeah.
intelligence. Um yeah, this has been a debate for a long time. What was your question? Is it in higher position? From a goal perspective, of course, yes, because AGI means that sometime a robot is becoming as intelligent as humans in understanding present situation, working with respect to that. If you are asking like whether we are already there, it's my personal view. I think we are not, and it's not too soon either.
Okay. Any other questions, participant? Okay, there's a question. Can I can I turn the prompt to become intelligent if it helps a model think better than it was trained to?
Can a tune prompt become intelligent if it helps a model think better than it was?
Trained to.
Yeah, I mean, like, yes, you are adding some more capacity to the model during your prompt tuning. But if you are really thinking if it is adding the intelligence to the model, that basically means that the prompt tuning that you are doing is for a niche task or a different task that the model was not good to begin with. So, in that sense, yes. But as far as the world knowledge is concerned, its own parametric knowledge that doesn't get changed via prompt tuning. The prompt tuning is more towards aligning to a task. So you are right. You can teach the model to be much better at a certain task. So in that sense, it does become more intelligent, but it doesn't change the parametric knowledge it has.
Okay. Difference between AGI and ASI.
Truly, I don't know. I haven't really heard of the term ASI as often as you have. Maybe I thought AGI and ASI are same.
Yeah.
But yeah.
Sujan from Webco, you are asked to unmute. Can you speak? You're continuously raising your hand. No, that try. Okay. Next question, sir. What could be your advice as I am now learning ML, then like to go for AI agent, agentic AI.
So I would say everything, be it agentic or non-agentic. Why I am saying this is There has been a lot of noise around agentic for last 2 years, but again, a personal opinion, agentic is more of a wrapper over LLM. Agentic world cannot survive without very good LLMs that is backing those operations. And all of this, I mean, a lot of the noise that you keep hearing around agentic is around tool building. These are frameworks. These are developer friendly frameworks. These are no fundamental improvements. I mean, the fundamental improvements are happening in the research world, which is trying to make LLMs more readily consumable by agents, not by the agent tooling that you are hearing the noise about. So if you're trying to go towards agentic, remember you have to be expert on LLMs to make any innovation, and the agentic tools are just feeding on top of it, nothing more. So 2 years down the line, I don't know whether the agentic bubble will burst, but the LLM is going to stay for a long time. That I'm sure of.
Any other questions? Okay, sir, we'll go for the quiz now.
Sure.
Harry, can you paste the slide up this link? Request the participants to join the Slido quiz. It is a time-based quiz. We will have 20 seconds to answer the questions. For each question, you have 20 seconds. The fastest will be in the leaderboard. Total of 10 questions will be in the quiz. Each question, there will be a leaderboard. Okay. Harry, have you pasted the link?
Yes, sir.
Okay. The link has been pasted in the chat box. Request the participants to use the link and register in the Slido quiz. My screen is visible.
Yes,
Okay.
127 have registered into the quiz.
Okay.
Joining the
Once
quiz.
it reaches to 250, we'll start.
300 also. 433.
Request the participants to join soon in the
Yeah,
Slido
we are
quiz.
waiting
Please.
for you to join. Please do that quickly.
In 1 minute, we can start.
Only said 200, 250. Please join quickly.
Okay, now I'll go for the first question. It is a timed quiz. We'll have 20 seconds for the question. Okay, the first question. What does a language model do? We have 4 options to answer. Okay, 74 of the participants have answered C. Okay, C is the right answer. The second question. What is not true about the transformers in NLP tasks? Okay, it is a mixed response. We'll see. Okay, 54% of them got the right answer. The third question. Which of these tasks can be done through task-specific fine-tuning of a LM like grid? Okay, all the above is the common answer. Okay, 73% of them got the right answer. A fourth question. Which of the following was an emerging property of LLM? Okay. Okay, A is the right answer. The fifth question. I request the participants after answering the question to come to the Zoom screen. You are now in the web screen. I request the participants to come to the Zoom screen. We will have the leaderboard. Let's have the leaderboard after this question. Okay. Now the leaderboard. Okay. Anbarasi from Lizard got 5 answers in 36 seconds. Shivakavi got 5 answers in 42 seconds. Antonita got from Lizard got 5 answers in 48 seconds. Chandra Prasad got in 49 seconds. Danush from I don't know which college, 50 seconds. Okay, I request participants come again to the web screen. I'll go for the sixth question. Okay, for the sixth question. Which of the following is a false from prompt tuning? Okay. Okay, B is the right answer. Seventh question. Which of this is a benefit from RAG? Okay. D is the right answer. Eighth question. Okay. Ninth question. Okay, many mixed answers. Let's see. Okay. A, B, C are the right answers. It's a multiple choice question. Okay, 10th question. Where in RAC can LLMs be used? Okay, the quiz has now ended. Now I request the participants to come to the Zoom screen. We'll see the final leaderboard. Hope you all came to the Zoom screen. The final leaderboard is okay. From second place, Sivakavi came to the first place. Ajay answered in 1.40 seconds. Hari is answered in 1.42 seconds. Chandra Prasad remains in fourth place. Jashwant, I don't know from which college you are. You answered questions in 1 minute 55 seconds. Thank you for attending the quiz. A small, sir, do you want to say anything, sir? Jaydeep, sir?
No, I'm just happy like most of the students got the quiz correct. That means like whatever we have been discussing has been observed.
Okay, thank you, sir.
300 of them have taken the quiz out of the 468, which is a good number. To have taken the bold step of attending something and looking at the results. Some of you might have got clarified as well about your thought process, I hope, by attending a quiz. Yes, Kishore.
Okay, there's an announcement regarding the next step of the lecture series. Now we have successfully completed all the 4 sessions of the Industry Astral Lecture Series by IBM Research. Thank you for your active participation throughout the program. As the final part of this initiative, we will be continuing conducting the online quiz on 20th September. The details will be shared soon through the email and in our WhatsApp group that we are maintaining. If you have not joined in the WhatsApp group, I request CRE to paste the WhatsApp group in the chat box. You can use that link and join. Students who have attended all 4 sessions and scored 90% or above in the quiz will be receiving a merit certificate as recognition of their achievement. We encourage all of you to participate in the quiz and make the most of this opportunity. Thank you once again. Now I request Ms.
Kishore,
Anuradha Ramanujam. Okay.
One question. If they have missed any of the session, they can go to the recording and still do the feedback and online test.
Yes, there is a separate link for the attendance marking in the recording session. They can write a mail and they can watch the recording.
So they must have registered, but right in the beginning.
Yes,
Otherwise,
yes. They can contact the coordinator.
Yeah, please contact the coordinator. If you have not attended any of the sessions, you can always go through the recorded link and complete the feedback and online test to become eligible for this particular 20th September test. So that will further qualify you and validate your understanding in this area. The very, very important basics have been covered in the first, the 4 sessions of this particular series. So I would encourage all of you to be eligible to take part in the third, on the 20th September test as well. I thank Jaydeep. It's more than a custom to just thank, but deeply indebted to your knowledge and your passion to deliver the same, to deliver it across to so many colleges that have come. If they had listened to us and put the prefix the colleges, you would have been able to see how many colleges have actually participated in this. I think at least 20 to 30 colleges from a variety of places, right from Tamil Nadu, Andhra Pradesh, Telangana, Kerala and Karnataka would have participated in this particular session. PALS is now a 75 member, I think 70. We are racing towards 75. The number is 75 colleges which are part of PALS. And we really hope and pray that very useful interaction with the IBM Research Lab, which is a global entity for all the others. It's coming just served on a platter, and the best of knowledge is delivered to you. And I hope this will be your RAG. Actually, this will be your storage of knowledge. Even if you go through these 4 sessions, you will be there. And whatever you want to do, money, for instance, he was asking whether logic is important or the numbers are important. I would say both are important, and more so logic is most important with AI. And number is just to verify and validate whether the machine has done the right thing for you. So I encourage all of you to take deep interest in this particular area and make use of it in whichever field you're going. I want you to use these kind of knowledge that you gathered outside your college from the best of experts. Thank you all for attending, and thank you, Kishore and team, for doing a wonderful job at the back end.
Thank you, Pulse team, for arranging it.
Thank you, sir. Thank you.
Thanks.
Thank you, participants. We have pasted the feedback links in the chat box. I request all to mark your feedbacks. Thank you, madam.
Thank you.
Thank you, sir.